course, with pleasure. So the work we are conducting here at XFEL concerns the chemistry of carbon nanoparticle formation. It is a very important topic because it's linked to pollutant formation and emission from combustion devices. And we well know that the presence of carbon nanoparticle in the atmosphere are well linked to adverse hazards to health, human health, and environment. From a chemical point of view, the formation of carbon nanoparticle is a very complex process which involves several multi-step processes and multi-physical processes. And some of these steps are relatively well understood. For example, the formation of the gas phase precursor of the particles, or the particle growth and oxidation. And this is because we have instruments, experimental and theoretical, that are able to study this kind of processes. On the other hand, other steps are really not well understood. And one of these steps is the nucleation part. So the nucleation of carbon nanoparticle is essentially the step that brings from the gas phase to the solid phase state. And so it's the appearance of what we call the primary particles, which are 1 to 10 nanometer particles. And there are no real conventional experiments that can probe this kind of species, or solid state species. So the focus of the research here at XFEL is really to try to understand and to monitor for the first time this kind of nucleation process. Yes. First of all, I would like to mention that this study is performed with the unique apparatus that we developed in France at CNRS. It's on my back, and it is the high repetition rate shock tube. So shock tubes are apparatus where the thermodynamic condition of a mixture is brought to certain conditions which are relevant to combustion devices through the propagation of the shock wave. It's an instantaneous heating and increase of the pressure, and the thermodynamic condition of the gas stays constant for a certain amount of time, during which we can do our study, our analysis, our monitoring, our diagnostics. Normally, conventional shock tubes are very large apparatuses, let's say, several meters long, and we can run one experiment per hour. Okay? With the high repetition rate shock tube, we can go up to 2 Hertz, so 2 experiments per second, because it's fully automated. And so we can run many shocks at the similar conditions, and then do signal averaging, and this allows us to use the detection techniques that are at XFEL. Once we are able to set up this apparatus at XFEL, we can use their diagnostic at MID, in particular the small angle scattering, to monitor and probe time history of the formation of the first nanoparticles down to 1 nanometer. And this only thanks to the characteristic of the X-ray beam here, that we will be able to monitor these small particles in real time, with a very high resolution in time and over a large domain of time, which is the kinetic time of formation of these particles. There is no other instrument that can do this. Well, there are several applications. So first of all, as a scientist, from a fundamental point of view, this kind of experiments have never been attempted. And so we will be able to respond to long-standing questions concerning the nanoparticle chemistry. From a practical point of view, we can use the results to develop detailed, comprehensive, and very predictive chemical kinetic models for the formation of the entire nanoparticles. And these kind of models, they can then be used for several applications, as I said. First of all, for example, for the optimization of the next generation combustion devices to reduce pollutant emission, or for the flame-based synthesis of carbon nanoparticle and nanomaterials, or for example, for an industrial safety application and simulation of flame propagation in fires, for example. So essentially, all these results will give us the tools for the development of cleaner, more efficient, and also safer combustion technologies.